Hi, this is Yinghao. Today I'd like to present our work in progress on EMERGE, which stands for Enhancing Multimodal Electronic Health Records Predictive Modeling with Retrieval-Augmented Generation. This research is a collaborative work between Peihang University, Peking University, ETH Zurich, and China Mobile Research Institute. So now let's begin. Here's the outline, the structure of today's presentation. First, let's begin with the background. What is electronic health record EHR data? EHR data can take many different forms, including text, time series data, tabular data, images, and videos. This data is considered multimodal, meaning it comes from various sources and has different formats. Additionally, EHR data is often irregular and longitudinal, as it is collected continuously over the course of a patient's care. It is also frequently sparse and high-dimensional. In our research, we focus on the multimodal characteristic, mainly concentrating on textual clinical notes and time series longitudinal EHR data. As we have mentioned on last slide, our work is for multimodal EHR learning, primarily for enhance its performance on downstream tasks. Current existing multimodal EHR predictive modeling work generally applies deep learning-based approaches. However, there's a significant challenge we need to address. Unlike healthcare professionals who have extensive knowledge and experience in medical contexts, neural networks trained from scratch lack this inherent understanding of medical concepts. This is a crucial difference that impacts the effectiveness of these models. Without deliberately integrating external medical knowledge, these neural networks often struggle to recognize important disease entities or interpret laboratory test results within the EHR data. This limitation can significantly affect the accuracy of prediction tasks that are essential for patient care. Given this context, our primary objective is to explore how we can better incorporate external medical knowledge into multimodal EHR modeling frameworks. Let's dive into some key limitations of previous approaches in multimodal EHR analysis. Limitation 1. Previous methods integrating external medical knowledge into EHR data analysis focus more on structured data, for example, ICD codes, drugs, procedures, and often neglect unstructured clinical notes and time series data. Limitation 2. These methods primarily extract hierarchical and structured knowledge from clinical context knowledge graphs. However, these medical concepts, entity names, and their relationships into a graph have limited direct contribution to predictive tasks. Limitation 3. Approaches like GraphCare, which use large language models to generate medical knowledge graphs, suffer from hallucination issues and domain gaps. In short, recent efforts integrate external knowledge like knowledge graphs to enhance model interpretability and performance, but face challenges in effectively linking multimodal EHR data with external sources. To overcome these limitations in previous works, we propose utilizing LLMs in a retrieval-augmented generation approach. The RAG framework integrates structured time series EHR data, unstructured clinical notes, and an established KG'-KG with LLM's semantic reasoning capabilities. The LLMs are prompted to generate comprehensive summaries of patients' health statuses, and these summaries are then fused for downstream tasks. Despite its apparent simplicity, applying this method to clinical tasks presents several technical challenges that need to be tackled. Challenge 1. How to extract entities from multimodal EHR data and match these entities with external KG consistently. Extracting entities from the diverse and complex formats of EHR data, including clinical notes and multivariate time series data, is challenging. Moreover, unlike structured codes where it can directly compare the code-related entities embedding with KG's entity, the entities extracted by LLM have hallucination issues. Accurately matching extracted entities with those in an external knowledge graph while eliminating the potential for hallucinations posed by LLMs is crucial for maintaining the integrity and reliability of the clinical prediction tasks. Challenge 2. How to encode and incorporate long-text retrieved knowledge with task-relevant characteristics. The extracted textual knowledge likely contains too many tokens for conventional language model inputs. For example, BERT supports only 512 tokens. However, with the development of long-context LLMs, it is feasible to leverage LLMs to distill this knowledge further. Additionally, simply integrating the retrieved knowledge may not be task-specific, creating a gap between the knowledge and downstream tasks. Therefore, a task-relevant prompting strategy is necessary during the LLM distillation process. Let's walk through the overall architecture of our proposed Emerge framework, which integrates multimodal EHR data with external knowledge. Starting at the top, we have the time series data, denoted as XTS. This data is structured into multiple visits, each containing various features. We use a GRU to process this sequential data, producing a time series embedding HTS. Simultaneously, we extract abnormal features from the time series data using z-scores. These extracted entities, along with disease names extracted from clinical notes using an LLM, feed into our retrieval generation pipeline. In the retrieval phase, we match these extracted entities with nodes in our knowledge graph using entity embedding similarity. A threshold is applied to filter the entities and retrieve relevant information. Moving to the generation phase, we use an LLM to generate a summary of the patient's health status. This process integrates the extracted entities, retrieved nodes, and triplets from the KG, guided by a carefully crafted prompt. The generated summary is then encoded by a language model to produce the RAG embedding, HRAG. At the bottom, we have the clinical notes, XNote. Disease names are extracted from these notes using an LLM, and the entire text is encoded by another LM to produce the note embedding HNote. Finally, all three embeddings, HTS, HRAG, and HNote, are fed into a multimodal fusion module. This module combines the information from all modalities to produce a final representation, Z, which can be used for downstream tasks like classification. Let's dive deeper into how we process and extract information from the time series data in our Emerge framework. On the left, we see our overall architecture, which we've discussed previously. Let's look at the right side of the slide, which illustrates our process for extracting and enriching information from the time series data. First, we extract abnormal features from the time series data using z-scores. We set a threshold value of 2 for the z-score to identify these abnormalities. In our example, we see that blood pressure is too low and blood urea nitrogen is too high. Next, we match these extracted entities with nodes in our knowledge graph using entity embedding similarity. This step helps us link the abnormal features to relevant medical concepts. We then refine these entities by prompting a large language model for more accurate retrieval. This step helps to reduce potential errors and ensure we're working with the most relevant information. For each matched entity, we store comprehensive information, including its name, definition, description, and disease relationships. In our example, we see detailed information for hypotension disorder and uremia, including their definitions and descriptions. Finally, we extract disease relationships from the KG, as shown in the bottom right. This gives us a network of related conditions that might be relevant to the patient's status. This process allows us to transform raw time series data into a rich, context-aware representation of the patient's health status, incorporating both statistical anomalies and expert medical knowledge. Now, let's turn our attention to how we process the clinical notes. The key innovation here is our use of large language models, prompting the LLM to extract task-relevant entities from the unstructured clinical notes. With extracted entities, the following steps are the same as in the time series modality. Next, let's focus on a crucial step in our Emerge framework, the generation of a comprehensive patient health status summary. This step builds upon all the information we've extracted and processed from both the time series data and clinical notes. The key to this process is our carefully designed prompt template, which you can see on the right side of the slide. Let's break down this template. Role and instruction. We start by giving the large language model a specific role, that of an experienced clinical professor. We then provide clear instructions on what information is available and what kind of summary we want. Extracted entities in time series. This section includes potential abnormal features identified from the time series data, such as blood pressure too high, blood urea nitrogen too low. Extracted entities in notes. Here, we list the potential diseases extracted from the clinical notes, like headache, flu, chest pain. Retrieved KG nodes. This section provides definitions and descriptions of the relevant diseases pulled from our knowledge graph. This gives the LLM context and detailed medical information about each condition. Retrieved KG triplets. Finally, we include disease relationships extracted from the knowledge graph, providing a network of related conditions and factors. This summary is designed to be informative and beneficial for various healthcare prediction tasks, such as in-hospital mortality prediction and 30-day readmission prediction. For the multimodal fusion module, we design a simple cross-attention-based network that incorporates the generated summaries and adaptively fuses multiple modalities for further downstream tasks. We start by text fusion, which combines the text embeddings H-note and H-rag. Then, a bidirectional cross-attention mechanism is employed to attend to the text embedding and the time series embedding. The outputs of these cross-attention operations are then concatenated and passed through a feed-forward network. We conducted our experiments using two major datasets and focused on two critical healthcare prediction tasks. The datasets are MIMIC-3 and MIMIC-4, both widely used in healthcare research. Our tasks were in-hospital mortality prediction and 30-day readmission prediction. In addition, we used PRIME-KG, a medical knowledge graph from Harvard, which provides our model with a rich source of external medical knowledge. Now for the experimental results section, let's examine the question: can our eMERGE framework outperform existing approaches in multimodal EHR analysis? The answer is yes, as shown in table. eMERGE consistently outperforms all baseline models across both datasets and both prediction tasks. We then conducted ablation studies to examine the role of the proposed modules in the model's performance. We looked at the performance of individual modalities and their combinations. The results show that combining modalities from time series data, clinical notes, and the RAG pipeline improves performance compared to using individual modalities. Regarding the modality fusion strategy, our designed cross-attention-based fusion network also performs slightly better than simpler fusion approaches. From the figure, we compare the performance of 4 different time series encoders: GRU, LSTM, Transformer, and RNN, in encoding EHR data. The evaluation focuses exclusively on time series data inputs, excluding any text inputs, to determine which model is most effective in handling such data. The GRU model consistently performs well, therefore we have selected GRU as the backbone encoder for time series data in eMERGE. Similar as modality fusion, we conduct the comparison for multiple text fusion approaches: node-only, summary-only, add, concat, adaptive concat, and MAG. The evaluation focuses exclusively on text inputs with no time series data. The concat strategy performs the best on the MIMIC-3 model and shows decent performance on MIMIC-4. Considering its simplicity, we choose concat as the text fusion method. To evaluate the robustness of our eMERGE framework against data sparsity, we conduct experiments using 1%, 20, 40%, 60%, and 80% of the training set. As depicted in the figure, eMERGE shows remarkable resilience, especially with only 1% less than 150 of the training samples. This robustness is crucial in clinical settings where data collection is often challenging, making eMERGE valuable for clinical practice. To conclude our eMERGE framework, a RAG-driven multimodal EHR enhancement framework for clinical notes and time series EHR data. eMERGE leverages the capabilities of LLMs and professionally labeled large medical knowledge graphs. We retrieve medical entities by prompting the LLM for clinical notes and using Z-score-based filtering for time series data. Then match them in KG with post-validation and alignment to mitigate hallucination. In addition to triples of entities, we also include more knowledge by extending the entity's definition and description. Methodologically, we first compare LLM-generated entities with original clinical notes to ensure the entities appear in the raw text. We then compute their embeddings and cosine similarities among extracted entities and KG entities, aligning the entities through threshold-based filtering. This ensures that the overall entity extraction and matching process adheres to clinical standards with consistency guarantees. We prompt the long context LLM to summarize the extracted knowledge into a distilled reflection of the patient's health status, instructing the generated content is task relevant. To integrate the extracted knowledge and consider heterogeneity, we design an adaptive multimodal fusion network with a cross-attention mechanism that attentively fuses each modality's representation. Experimentally, our extensive experiments on the MIMIC-3 and MIMIC-4 datasets, focusing on in-hospital mortality and 30-day readmission tasks, demonstrate eMERGE's superior performance and the effectiveness of each designed module. Additionally, to meet practical clinical needs, we evaluate the model's robustness with fewer training samples, showing Emerge's remarkable resilience against data sparsity. Thank you very much. For any questions, please feel free to contact the lead author, Yinghao Zhu, via email. For more updates, you can check the website. We have also attached a QR code, which you can scan to access the archived version of the paper.